Well, many times in chemistry, we probably wonder, why are we learning this? Or how is this applicable? Or where will I use this? Today's lesson, we're going to be determining magnitudes and units of rate constants. And it sounded so very vague, and I knew that it would probably lead you to those thoughts at the very beginning of the lesson. So let's get started with a why right away. So I have this quotation right here. It comes from a, pretty prestigious textbook on chemistry, the central science. If chemists want to compare reactions to evaluate which ones are relatively fast and which ones are relatively slow, the quantity of interest is the rate constant. A general rule is that a large value of K, 10 to the 9th power or higher, means a fast reaction, and a small value of K, 10 or lower, means a slow reaction. So I hadn't given much thought to it, but I realized that these K values are actually given quite frequently when you're looking at reactions before you conduct them. Usually when you're looking in a lab manual or at procedures, there's a K value somewhere there, and I hadn't given much thought as to why it was there, but this really sums it up. It gives you an idea of how long you're going to be standing around waiting for this reaction to proceed, and it also gives you an idea that if it's going to be slow, what are some things that I can do to increase the rate of this reaction. So what we're going to start off with today is determining the units of rate constants based off of their rate law. So I've got my first reaction right here with the rate law written to the side, and I want to figure out what are the units on this K value right here. So in order to do that, I'm going to just substitute in units for what I do know. I know that my rate is in units of molarity per second. That's what a rate unit is. So my rate constant, I don't know the units for, but I know that it's being multiplied by the units of concentration, which is molarity, just capital M. So I'm going to treat this like an equation where I'm trying to solve for K. If I wanted to solve for K, I would divide both sides by my molarity. Now this would make a complex fraction, which can be kind of confusing. So instead of thinking of it as division, let's think of it in terms of multiplication. Let's multiply by 1 over molarity. And that's the same thing as dividing. So I'll do that on the other side. Let's multiply by 1 over molarity. And that makes it a lot simpler because my molarity is going to cancel out here, and I'll see that my molarity cancels out here as well. So I end up with 1 over seconds. Is my unit for this rate constant. I could also rewrite this as an inverse second, seconds to the negative 1 power, and I'd be saying the same thing, that these are the units for this rate constant. Let's try another one. This rate law involves two different reactants. So when I write my equation, I know that for my rate law, my equation is going to start with molarity per second. K is an unknown unit, and it's being multiplied by a unit of molarity for my concentration of hydrogen, and then it's being multiplied by another unit of molarity for my concentration of iodide. So this is essentially saying that molarity over seconds is equal to my rate constant times molarity squared. So once again, I could divide both sides by molarity squared, or I could think of this as a fraction, multiplying by a fraction, and that's going to make my math on the other side simpler, so that's what I'm going to do. I'm going to end up isolating K, and there are going to be common terms that cancel out. However, they're not going to completely cancel out. I'm still going to be left with 1 unit of molarity in the denominator. So I'm going to end up with a unit of 1 over molarity times seconds for my units for my rate constant. Now this is a really messy way to write this. So what you'll commonly see is inverse molarity, inverse seconds are the unit for this rate constant. And then down below, our last one, this one's probably going to be the trickiest one. My rate is molarity per second. My rate constant is an unknown. It's being multiplied by a unit of molarity. And then it's being multiplied by another unit of molarity, but it's being raised to the 1/2 power. So when I combine these terms, I'm going to have molarity over seconds equals my rate constant times molarity to the 3/2 power. How did I get this? Well, this has an exponent of 1. When you're multiplying two numbers with the same base but different exponents, you add their exponents together. So 1 plus 1/2 gets me 3/2. So now I'm going to multiply by 1 over molarity to the 3/2 power on both sides to isolate my rate constant. And what I'm going to end up seeing over here on the left side is that there is going to be canceling, but it's not going to be complete. One of the molarities is going to cancel out, but I'm going to be left with a molarity to the 1/2 power. So I'll have 1 over molarity to the 1/2 power times seconds is my unit for my rate constant. Now, once again, this is a very messy way to write this. So it will usually be written as molarity to the negative 1/2 power, seconds to the negative 1 power.